We will now continue with building the equations of motion. Previously, we had plotted position time, velocity time, and acceleration time information. With the acceleration was a constant, the final velocity was equal to the acceleration times time plus the initial velocity, and we were left with no equation for the position. We know from mathematics it must be in the form ax squared plus bx plus c. But where do the a, b, and c come from? What we're going to do to consider this is we're going to come at it from a different viewpoint. Instead of starting with position, we're going to start with acceleration. And so if I plot an acceleration time graph for some acceleration a, as we saw before, the acceleration is going to be a constant. So the final acceleration is equal to the acceleration in the beginning. What we can now do is we can consider the area under this curve. And the area is going to be defined by going to the acceleration in the y and to some time t prime. And the acceleration is simply a rectangle, so it's going to be the acceleration times time prime. But acceleration times time simply describes a velocity, or more specifically, a change in velocity. If we calculate several of these, it will allow us to build up a velocity time graph. And if we plot our velocity time information, what we're going to find is a linear relationship. In this case, we're going to set v0 equal to 0. However, v0 can be any velocity that exists. We see that the final velocity is going to be the acceleration times time. And once again, we can calculate area. Only now it's not a rectangle, it's a triangle. So the acceleration is going to be equal 1/2 vf multiplied by t prime. And that's going to give us a change in position. Similarly, we can calculate a number of different positions, and then we can plot a position time graph. And if we do this, what we're going to find is we get the expected curve that we had seen previously, indicating that we have accelerated motion. Once again, we're left with the question, how are we going to develop the equation? Well, we know from what we've seen before that we must have a v0 times time plus an initial position, but we're left with how do we deal with the t squared term? Well, there must be some number in front of there, which must come from the initial conditions. And so we know that what we have previously is that 1/2 vf times t, and the vf came from the acceleration time, so what we're left with is 1/2 att, or 1/2 at squared. Using this information, we can write down our equations of motion. First, the acceleration. The final acceleration is the same as the initial acceleration, so this is a constant. If we consider the final velocity will be equal to the acceleration times time plus the initial velocity. This gives us a linear relationship. And finally, the final position is equal to 1/2 the acceleration times time squared plus the initial velocity times time plus the initial position. And here we have a quadratic relationship. And these are the equations of motion. In the event acceleration is equal to 0, we find the at term in vf goes away, and what we have is constant velocity. And if we have constant velocity, what we're left with is the acceleration term drops out, and we're left with a linear relationship. Similarly, if v0 is 0, then what we're going to find is both of those terms drop out, and we have the object stays in the same spot forever.